We have quite a few programs. If you're interested, please go online to www.mmc.edu, or you can look up saxmeharry.org and find out more about our programs. This fall, we're starting 4 new programs in addition to the 2 master's and 2 PhD programs we have right now. Certainly, there are excellent programs at Tennessee State University and our colleagues here in the Nashville area. Many opportunities to learn and develop your skills for AI and ML. And this is one activity here, this workshop, where I think you can really kind of get a fast overview of what the math looks like for AI and ML. Today is mostly fundamental concepts with mathematics and linear algebra, but I think tomorrow they're going to have some presentations on transformers and some of the newer technology that you'll see coming to the forefront. Mathematics is one of these languages that helps us understand how to wrap our minds around artificial intelligence and machine learning. I have had the pleasure of teaching math for about 10 years now. I'm not as advanced as some of the professors you'll see here who actually are math professors. So I'm honored to be in their presence. But it truly is the language that we speak now in order to be effective in the STEM fields, especially AI and ML. I have told my students on many cases, if math seems hard initially, then just practice and practice and practice. And it's kind of like playing a musical instrument. The more you practice, the easier it will get and the better you will become. At least that's true for most people in my experiences. So welcome today. And I hope to cover some of these topics in this 3rd section. And this is an overview, but I believe they're going to share the slides afterwards. So if you want to get a copy of these after we've done some edits, then that may be feasible. Let's see if I can. Okay. So this is part 3. And this section is going to talk a little more about some of the deeper aspects of linear algebra. And we'll kind of pick up where Dr. Setman left off. Let's see if I can change slides here. First button? Okay. So, not sure why the mouse is misbehaving. There we go. Okay. So I've now hopefully figured out how to run the mouse. Okay. Okay. We're getting close now to the beginning of the presentation, but it seems like I keep going backwards. So let me see if I can go back to the beginning. So just as a reminder, this second slide tells you a little more about myself, and you'll see that in the bio sketch handouts that you got from the workshop team. So let's see if I can navigate the clicker here. This part 3 is going to talk more about the eigenvalue and eigenvector problem that we kind of saw briefly discussed. And we'll also talk more about the matrix decompositions In particular, we'll discuss the LU decomposition, singular value decomposition, and the skeleton decomposition. These techniques are really kind of the strong points that you need to master to really advance yourself in concepts in linear algebra. And we'll talk more about these as we go through them. So maybe it's working now. One of the ways that I've really strengthened my knowledge of mathematics and linear algebra is to use some software tools. And if we have time, we'll talk about a Jupyter session that I've recorded in a PDF using Julia. Some of you may not have heard about Julia. It really does attempt to solve some of the problems that we deal with now if you're an active Python user or if you've been using other languages. So let's start out with the eigenvector problem. If we assume A is a square matrix and X is a non-zero vector, we are interested in all vectors AX that are parallel to X. And if we embody this in mathematics, we would write AX is equal to lambda X. So X is going to be a non-zero vector in the space that we heard discussed earlier. And if we can solve this equation, then lambda will be one of those eigenvalues that solves this problem. These are special vectors, and most vectors are not eigenvectors in general. Lambda denotes that AX equals lambda X is the so-called eigenvalue associated with the eigenvector X. So there is a special note here at the bottom on singular matrices. If A is singular, that is, if the null space of the matrix A is not equal to the empty set, then AX equals 0 for some elements of X that are found in the null space of the matrix A. In this case, lambda equals 0 for all such vectors. So what this is telling us is that essentially when we have matrices that are not full rank, then we're going to have some of those extra dimensions that Dr. Setman spoke of, and those would contribute to the zero eigenvectors, the zero eigenvalues when you solve the eigenvector problem. So how do we solve this equation, you ask? If we're given AX equals lambda X, then we can combine these terms to the left-hand side of the equation, and then we'll have A minus I lambda in parentheses multiplied times the X vector. Here in this equation, the I represents the matrix which has ones on the diagonal. So it's the identity matrix. If you think about the implications of this equation, A minus I lambda quantity times X equals 0, this suggests that if X is one of the eigenvectors that solves this equation, let me select this, then apparently the eigenvalue associated with this solution is going to be 0. And this implies that the determinant of A minus I lambda must be 0 so that we may have a non-zero solution X. So the premise is you require that X vector not be a 0 because you don't want a trivial solution. And that requirement then allows you to deduce that the determinant of A minus I lambda must be 0 so you can solve that polynomial of the characteristic equations. So if you've never seen this, if you've never done some examples, it's worthwhile to practice, get MATLAB or Julia or Python, your favorite language, and see if you truly understand the concepts before you move forward. So here's an example. Here we're given the challenge of finding the eigenvalues and eigenvectors of the matrix 1, 0, 0, 3. So this is a 2x2 matrix. It should be fairly easy. We start by forming a new matrix by subtracting lambda from the diagonal entries of the given matrix. And that's because we remember the equation from the prior slide that said the determinant of A minus I lambda must be 0. So we're going to subtract lambda using the identity matrix, and that means that only the terms on the diagonal of the A matrix are going to be affected when we do the minus lambda term. And so we can easily right away, if you remember the definition of determinant, we can compute this, and it gives 1 minus lambda quantity times 3 minus lambda quantity. And apparently, for this problem to be solvable, this must equal to 0. So therefore, we recognize this as a second order polynomial equation that can be solved readily. The roots are already collected in parentheses, and we see the roots are lambda 1 equals 1 and lambda 2 equals 3. So if we follow this through and we substitute in those eigenvalues to this matrix equation, the first one was lambda equals 1, and we can put that into the equation. Substituting as such, we have 1 minus 1 is 0, and the first upper left term here, and we have 0, 0, and then 3 minus 1 in the lower right, and that just gives us the number 2. The null space of this matrix is therefore the column vector 1, 0, and if you can tell, if you were to multiply this into the original matrix A minus I lambda, that this indeed would be an eigenvector, and you should find that the eigenvalue is 1. And you could do this with pencil and paper, or you can do it with MATLAB and your favorite scientific language. Same thing with lambda equals 3. We basically solve this system of equations by inserting the value of lambda, and when we do, we find the null space gives us this column matrix 0, 1. So if we want to check this, and that's what I was referring to earlier, down at the bottom here, we can just solve the equation A lambda 1 equals lambda 1x, and we see that indeed it holds true and it is a valid solution. Same thing with lambda equals 3. We repeat the process. We find that the solution holds. So if you've never seen this kind of problem before, it might be worthwhile to do some additional reading and follow through with this, because these problems really are kind of readily found and often found in problems in AI and ML. So here's another example. And you'll notice with this one, it's a 3 by 3 matrix, so it's a little more challenging. If it's a full rank matrix, and then we might expect we would have 3 eigenvalues. And we go through this example solution. We insert A minus I lambda for the left-hand side of that equation we're solving. We compute the determinant. That's what you see here. Lambda minus 4, lambda minus 3, lambda minus 1. We set it equal to 0, so we're solving this polynomial, and right away we can pick out the roots from this characteristic equation. They are lambda 1 equals 4, lambda 2 equals 3, lambda 3 equals 1. And so these are the eigenvectors. I'm sorry, eigenvalues. And so we can go through again and verify and validate that each one of our constructed solutions actually holds. And then when we put it into AX equals B equals lambda X, that it is indeed a solution. And this helps you verify that what you're thinking and what you're doing mathematically are actually valid. So I would encourage you to try this with your favorite software language and get some hands-on experience. If we have time at the end of this session, I'll discuss a little short example I did using IPython, Jupyter, and Julia language. So let's look at some other aspects of what we find here dealing with eigenvalues and eigenvectors. If we take the trace of this square matrix, and so far with this set of slides I've been discussing, you'll notice that these have been square matrices, and that does make a difference if you are doing this analysis. When we have matrices that are not square, that means the number of rows and columns are not equivalent, we'll have to use a different technique to solve this eigenvector eigenvalue problem. It's called the singular value decomposition, and that will be part of this discussion coming up. You'll notice at the bottom of this slide, we have the definition of the determinant in terms of the eigenvalues, and it is simply the product of all the eigenvalues, whereas the upper section gives us the trace is equal to the sum of the eigenvalues. So these can be used to help understand some of the particulars of the data that you're looking at and the eigenvector eigenvalue problem at hand. So here's one more example, unless, did I go backwards? No. So we compute the trace, and we just simply add up the elements on the diagonal. So that's for this A matrix at the top of the screen. The diagonal elements are 1, 3, and 4. We add those up, we get 8. For the determinant, we can multiply the eigenvalues, and according to the previous definition, that gives us the determinant values equals a scalar quantity, which is 12. Okay, so let's think a little more deeply about what's going on here. If we assume there are n linearly independent eigenvectors, x1, x2 through x sub n, of a square matrix, and this is really important that it's squared, let us put them as columns of a matrix S. And so now, if we think about what's going on here, we're using AX equals lambda X. That's our guiding equation. But now, on the left-hand side, we can group into this matrix bracket the x1, x2, dot, 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 x sub n, because those are all eigenvectors of the A matrix, presumably. We've solved the eigenvector eigenvalue problem. We know these are the eigenvectors, and so we put those in the bracketed term here on the left. On the right-hand side, we know that each one of these eigenvectors, when multiplied by the A matrix, will simply produce the eigenvalue times the original vector. And that's the beauty of the eigenvector eigenvalue problem. And so if we look at the right-hand side, I think you can see, maybe you can convince yourself that if we factor the right-hand side, then we can group all of the eigenvectors x1 through x sub n, and they would be multiplied by a diagonal matrix which has the eigenvalues on the diagonal. And so I think if you just do a couple examples here, if you take the first column, multiply times the matrix here to the left, then only the x1 eigenvector would be selected. Go down to the next vector here on the matrix to the right, which has all zeros, but it has lambda 2 on the diagonal. When that one multiplies to the matrix here on the left, it will select the x2 eigenvector, and so on and so forth. And we can then recognize that A times the S matrix is equal to S times the, I believe that's gamma. So this tells us that we can write in matrix format this eigenvector eigenvalue problem. And this can be very powerful, because if you look at AS equals S gamma, then we know that since S is full rank, we multiply both sides times S inverse. So S inverse on the left, S inverse on the right, and we are essentially able to solve for the diagonal matrix gamma, which is this upper hat Greek symbol, and that we can also solve for A in terms of the diagonal matrix and the eigenvectors. So what's very interesting and worthwhile to note about this is that this first version, S inverse A times S, is giving us a diagonal matrix. And if any of you are really fluent with matrix math and linear algebra, you know that anytime you have a diagonal matrix, it makes life a little bit easier, right? If you want to take the inverse of a diagonal matrix that has full rank and it has no singularities, then you just invert the elements on the diagonal. So let's see, we can do a quick example here. If we're using MATLAB, we can define the matrix A. And in this case, we have 1, 0, 0, 0, 3, 1, 0, 0, 4. And when we press enter, you would see this response. And we have a matrix. It's a 3 by 3 matrix. The eigenvalue function that's implemented in MATLAB is known as EIGS. So that stands for eigenvalues or eigenvectors. But you call the function on your A matrix and you put the two response or two return elements on the left. So in this case, we should return S and D on the left-hand side of the equal sign. And it also will print it to the screen and tell you that the S matrix has the form shown below, the D matrix, which is the eigenvalues, right? And then we can prove to ourselves that we've actually done the proper decomposition by doing the calculation to compute A that was shown in the prior screen. So you'll notice here at the bottom of the screen, we have A equals S gamma S inverse. And so that's what's done here in MATLAB at this last line. And all it does is reproduce the original matrix that we're decomposing. And so eigenvalue decomposition is a way to decompose a matrix using the eigenvectors from a well-defined problem. So Dr. Setman mentioned this a little bit earlier. This is kind of the next topic in this discussion. We're leading up to the singular value decomposition. Symmetric matrices are really important to machine learning. If any of you have done spectral clustering, or if you've done transition probability matrices and Markov stochastic chains, if you've done similarity calculations to compare, for example, using Pearson's correlation coefficient, you end up with an affinity matrix or correlation matrix, and those are usually real and symmetric. So this is a very important class of problems. We have the results in this slide that the eigenvalues of a real symmetric matrix are real. And there are proofs to support these. And the definition of the symmetric constraint is shown in the top line. If A equals its transpose, then that means that the matrix is symmetric. It also tells us in this number 2 bullet that the eigenvectors are orthogonal. That means that if we took the dot product of any two combinations of those eigenvectors, where the eigenvector combination is not against itself, then they will be, the dot product would be 0 because they are orthogonal. Okay, a matrix A having n linearly independent eigenvectors, we have A equals S gamma S inverse. So that is the way that we've shown earlier. We use the eigenvector, eigenvalue definition and the solution to get that solution. Number 4, the symmetric matrix A, we have A equals Q gamma Q transpose, where Q has orthogonal eigenvectors of A as columns. And so this is a really nice compact matrix factorization representation of our original matrix A, but we're now representing it in terms of the orthogonal eigenvector matrices and the diagonal matrix, which contains the eigenvalues on the diagonal. And the bottom line says that if we look at the spectrum of a square matrix, it is the multi-set of eigenvalues. So that's a really important concept. I may need to go a little faster here. So there's an example here of symmetric matrices. So it's pretty simple. You'll notice A and A transpose, they have the exact same values. So let's go on a little further. We want to get to this SVD definition and discussion if we have time. Positive, definite, symmetric. If all of these products of X and AX are greater than 0 for all X, this implies that all eigenvalues are positive. So I mentioned earlier, there's ways to prove some of these concepts about these real symmetric matrices. So since we're doing matrix decomposition or matrix factorization, one topic one method that is popular is LU decomposition. It's called lower upper decomposition, and it's based upon this observation that any matrix can be written as a product of a lower triangle and an upper triangle matrix. And so in the bottom, you'll notice this is basically matrix factorization, but it's done between two triangular matrices. One is lower and one is upper. So this is an important method that you'll want to be cognizant of when you think about how you can reduce the dimensionality of your problem at hand. And that's one of the things that really is driving a lot of this. We want to take problems that are in 10,000 dimensions and reduce them to meaningful matrix problems that are in lower dimensions that are feasible, that you can run on your laptop, maybe while you're doing your prototype. And we have an example here. These slides will be distributed. I'm going to jump on to the singular value decomposition. So this definition here that we're sharing arises largely from what's known as the fundamental theorem of linear algebra. And it's, I think, very instructive to try to learn as much about this factorization technique as you can. The reason this is important is you'll notice that it says any matrix A. It's not required to be square. It doesn't say that it has to be symmetric. And it may or may not be full rank at this point. We really haven't put any constraints on it. If we look at the terms for the right-hand side, U times sigma times V transpose, then we're looking at a process that mathematically looks like this exploded view where we have U1 through U sub M, we have sigma 1 through sigma R, and then on the right we have the elements of V1 through V sub N transpose. And so they're laying down like rows, because when you transpose a column, it turns it into a row, right? You'll notice that on the diagonal of sigma, we have sigma 1 through sigma R. But the rest of these elements are 0. Would anyone care to guess why we have some 0 singular values here on the diagonal? Why might that be useful? So we're anticipating that we could have a matrix that could have some 0 eigenvalues. It might, because it may not be full rank, or it may intrinsically have some multiplicity for the 0 singular values. So that is an important thing, I think, to take away with. The very bottom line says where U transpose U equals I and V transpose V equals I. This is a really nice mathematical way to demonstrate that these matrices U and V are have a unitary representation. In other words, when you take the dot product of these orthogonal matrices with themselves, they just give you the identity matrix. This presumes that those matrix vectors have been normalized so that you're going to get that identity matrix with elements on the diagonal. And it's a great way to check to see if your algorithm and your functions are working properly. There's an example coming up here that we can talk about. Before we get there, though, look at this version. It's called the skinny SVD. And it's essentially drops those zeros out of the diagonal of this matrix shown earlier. So if these are zeros, then that suggests that those may be associated with the redundancy that's built into our original matrix that comes from not being full rank. So if we want to just truncate the mathematics and only use the elements that are distinguished in the matrix that do not have 0 eigenvalues, then this would be the skinny version, and it simplifies some of the math so that we are taking advantage of those zeros on the diagonal of our sigma matrix. And so we have an example here. So in this example, the A matrix is defined 1, 0, 0, 0, 3, 1, 0, 1, 4. And so in MATLAB, we can compute the singular value decomposition by just using what's known as the SVD function. So you see the line up here. We have U, S, and V on the left-hand side. Those are the return arguments. Then we have the SVD of A. And as a result, MATLAB prints to the screen the U matrix, the S matrix, which are the singular values. And you'll notice it is diagonal. And then the V matrix. And presumably, the U matrix and the V matrix will satisfy that orthogonality and orthonormal constraints that will give us the identity matrix. And so indeed, when we check this in MATLAB, we find at the bottom that if we multiply U times S times V transpose, we actually recovered the original matrix. So that was what we advertised in the beginning. But if we also check U transpose U and V transpose V, we get the diagonal matrix. And you'll notice there are some asterisks that appear in this matrix. And I think there's a little more explanation if we go forward. Those are going to be associated with elements that were not computed because of the rank of the problem. So here's another example. And you'll notice this one, before they do the singular value decomposition in this problem, they compute the rank. And so it looks like it's a 4x4 matrix. But you'll notice if we ask MATLAB, what is the rank of A? It tells us the answer is 2. So that means that there are redundant rows and columns in this matrix that make it look like a 4x4 matrix, but in actuality, we might could reduce it to a 2x2 matrix where we've eliminated the non-linear dependent elements. I think I said that right. So in essence, A matrix is defined here. It has rows and columns that are not linearly independent. So that means they're basically redundant unless you're doing a special problem that requires those to be included. And again, at the bottom, we check to see if we recover the solutions as advertised. So there's a couple more things to look at here. Everyone doing good? Okay. Everyone can hear okay? Very good. So if we work through some of the math here, we use our knowledge of matrix axioms, we can take the calculation of A transpose. Remember, A was our original data matrix, but we can represent this product of A transpose A using the singular value decomposition. And so you may recall that when you take the transpose of, for example, A times B, you reverse the order and then you take the transpose of each term. So the first term is A transpose, and you'll notice if you take the transpose of U sigma V transpose, you will obtain V sigma U transpose. And that's the first term. The second term, it will just be U sigma V transpose. When you multiply these together, it gives you an interesting result because now you contract on the inner terms and you only are left with sigma squared on the interior of that product combination. The columns of V are orthonormal eigenvectors of A transpose A. So we know this. That's one of the constraints of solving the singular value decomposition is that U and V will be orthonormal. But if we look at the other combination, A times A transpose, we can compute that and it will eliminate the V's in the result, and we'll have U sigma squared U transpose. The columns of U are orthonormal eigenvectors of A transpose. We also can identify that apparently the singular values in our SV decomposition are really the square root of the eigenvectors associated with the A transpose A. So a pretty good way to relate this back to the eigenvector problem. So we have an example here. Before I go into this example, just briefly, I would note that if you have a square matrix, you can do matrix diagonalization with the eigenvector, eigenvalue equations and that theorem, and it should work fine. You may have some singularity observations in the decomposition, but if your matrix is not square, like in many real world cases, then you'll need to use the singular value decomposition, and those singular values on the diagonal of sigma are related to the eigenvalues from the eigenvalue problem on the earlier examples, to the extent that if you could make them both square, you do the SVD on the square matrix A, do the eigenvalue decomposition for the same matrix, you'll see the relationship between the sigma elements on the diagonal. So I'm going to go through a few more slides here and try to get to my Jupyter file if time permits. But just conceptually, what's going on when we multiply these terms? So we're looking at U sigma V. This is the definition. So what's really happening to this U times sigma times V transpose? Well, you can look at this figure on Wikipedia on the singular value decomposition page. They have the same figure. And so we can see that what's happening is these operations are acting as transformations on our original data. So for example, this one at the bottom, when we multiply by V transpose, it's creating a rotation in this two-dimensional unit disk. So the blue region is a two-dimensional unit disk in R2, right? So it's in the set of real numbers raised to the second power because it's a plane. When we multiply by the singular values in the singular value matrix sigma, it's going to do another transformation. So it looks like now the circle has been transformed to an ellipse, and then U will actually do a third rotation of that ellipse and give you the answer at the very top. So it's a pretty good way to think about what's going on. There's one final concept in matrix factorization that we want to talk about today, and it's called skeleton decomposition or CUR decomposition. Dr. Seckman and Dr. Aldruby have a really nice paper published on this. I'm still new to this, but it seems like it really has some great features and parameters that allow you to use this in a day-to-day fashion for dimensionality reduction. So it's known as CUR decomposition. You start out with a data matrix W, which presumably has three submatrices inside of that W matrix from our data. If we take the rank of the matrix and assign that to our parameter R, then we can write this decomposition as W equals C times A inverse times R. And we're going to try to explain what this is quickly. If you want more information, Dr. Seckman's paper is published online. It's open access. You can download a copy. We denote the matrix C as the R columns of W. So W may not be full rank, but if it's not, we're going to choose the columns of W that are linearly independent. Same thing with R, we're going to choose the linearly independent rows of W, and then we're going to assign A, the A matrix, to the intersection of the C and R matrices. And so there's a really nice example coming up here, and it may not be clear today. It's a little, if you never looked at it, it might be a little involved to see on the slide. But we start out with our W matrix, and then if you look through this is a conceptual, there's no numbers here, but it's a conceptual example. If we choose the columns here, this one, so that's the first, that's the second column, the fifth column, and the seventh column. Those, in this example, would comprise our C matrix. The R matrix, which are the row vectors, is going to be comprised of the second row, fourth row, and fifth row. And so this is how we figure out what the R and C matrices are going to be. Now, you may ask, well, what is A inverse? And so to get A inverse, we need to determine, well, what is A going to be? Now, this is not the same A that we necessarily had before. This is kind of a new version of our A matrix. And you'll notice the lines are picking the intersections of the rows and the columns out of the original matrix from our W data source. So all of these bold-faced circles end up mapping into the A matrix. And so if we have a matrix that is non-singular, then we can take the inverse, right? And so that implies that we could actually compute this estimated version of W equals C times A inverse times R. So pretty powerful and intuitive way to look at this problem. And I think we may see more applications for this in the future. There is a quick example here. You're given a numerical matrix W. Before we do any real analysis, we compute the rank, right? We see the rank is 2, and therefore we know that there are some redundant elements in this matrix. It tells us maybe the CUR could give us a way to reduce the dimensionality of the problem and improve our computational effectiveness. So the lines are drawn here to help us see the rows and columns. But I would just point out, in case Dr. Seckman showed some examples of this earlier, but you'll notice that column 2, let's see, column 2 and column 4 are not linearly independent. You all see that? Now, if we let's look for some rows that are not linearly independent. Who can find a row, or who can find 2 rows that are not linearly independent? 1 and 3. Very good. Very good. So right away, we see that there is redundant information in our data matrix, and the CUR skeleton decomposition will help us compact this representation to get our work focused on the real core of the problem and avoid these high dimensional irregularities that really may not add anything to your problem. And so one final example here using MATLAB. If we start out with this version of W, we can identify the 2 matrices for C, do the same thing for R. So we see the 2 columns that are linearly independent. We see the 2 rows that are linearly independent. And we can then choose A as the intersection. If you go back to this slide, so we choose this intersection. So from this example, we see 1, 2, and 0, 1 are going to be the intersection of C and R. In this example, it's the same result. This is just a numerical verification of it. Then we can see if we can recalculate the original matrix by C inverse A times R. And if you compare these two, the top W and the bottom calculated W, they look like they're identical, right? So it really has compacted the problem of our data set. And this is related to the subspace clustering and subspace mathematics that was discussed earlier. Okay, well, let me see if I can have one quick look at the you have to stop and share. See if I can show quickly the Jupyter slide that I brought. Stop sharing. So it's not exiting. Oh, here we go. There we go. I was pressing the wrong escape. You go to window. And then, yeah, thank you. Share. Okay, so so before today I prepared some simulations using Jupyter and Julia. Now, if you've not used Julia before in the past, you really owe it to yourself to take a look at it. It claims to be as fast or faster than all the other scientific computing languages. It's built on top of the LLVM infrastructure that Apple bought and open sourced, which is now the basis for most Apple products. It is the basis for the C-Lang compiler. It supports a virtualization technology that allows you to apply instrumentation to the execution of your code to optimize the performance. It also allows you to, in hardware and software, to implement automatic parallelization of most linear math operations, as well as for loops and other things. It's very high performance. If you go to julialang.org, I believe, they will show you a comparison to all the other languages. It includes a pre-compiler that pre-compiles all of your packages, and so they execute at almost metal speed, if you will. And one final comment is that it employs OpenMP. So if you have a CPU with 64 CPU cores, it will automatically parallelize your operations across those cores as threads, but it's completely seamless and transparent to the user. You do not have to write parallelized code in most cases. It will do it for you. So if you want to do matrix inversion or singular value decomposition, you can open up a console on your Mac or whichever machine you're using, run top, and you can watch all 64 of your CPUs run in parallel when you press enter to do matrix inversion. So it's very powerful. It's extremely fast in most cases, and it's a little young. It's about 10 or 12 years old. So if you get a bleeding edge version, there might be some bumps. But generally speaking, I've been using it now for 4 or 5 years. I use it in teaching classes. It's pretty nice, and I don't think you'll have too much trouble with it. So I coded up this example to demonstrate, and I got the idea from this off the internet. If you go to juliaimages.org, follow this URL, you can see the original source code. It's similar to this one. So the first thing we do is load some packages, images, test images, linear algebra. Those are all packages that you would import. If you were using Python, you would type import package name, right? Same concept, but in Julia, you just type using and the name of the packages. These are already installed on my system, so if you don't have them installed, it would give you an error. We load the test image. In this case, it's a monarch butterfly, and we decompose it's an RGB image, so we decompose the color channels, and then what we're going to do is create a function, and we're defining this function ourselves. It's called rank approximation, and what it's going to perform is the singular value decomposition it's going to use the singular value decomposition, to estimate the rank. And we just saw how that could be done in the formalism. Then you'll notice SVD factors, and there's the SVD command. It's going to decompose each one of those red, green, and blue color images, and then it's going to do a for loop. You'll see 10, 50, and 100, and it's going to do the rank approximation to the reconstruction of this image that is being decomposed from the singular value decomposition. And so the last line says VCAT, and when you're using Jupyter, this is a way to display the image on the screen. So what would happen is you would get these 4 images of the butterfly. And in essence, what we're doing here is we're reducing the dimensionality, we're reducing the rank of the original data matrix, but we're also, in a way, doing image compression. The image at the top left, I believe, is the original image. The one, the top right, is the rank 10 approximation. Bottom left is rank 50, and bottom right is rank 100. The original image, I believe, is 512 by 512. So that's quite a bit of dimensionality reduction. And you can see this, pictorially now by just looking at the picture. If we were doing this for purposes of spectral clustering or other techniques that were needed, we might not have this visual representation. But this, I think, is a good display of what's really going on if you want to try to visualize it. And then I have one more example. In the Julia ecosystem, there happens to be a package called low rank approximation. Low rank approximation. And so I load this low rank approximation package, then I generate a random matrix A, and then it has a function that allows you to do a ranked reconstruction using the skeletal or the CUR decomposition. So I create my U matrix, and I tell it I want a rank 11. So the original problem we know should have been, in theory, it would be rank 15 if those were all linearly independent. But I'm asking for a rank 11 estimation or approximation. And then it tells me that it's created the structure. It's a CUR packed matrix. And if you look at the first grouping, the 3, 8, 12, 11, those are the rows that it has identified to create the approximation. And so here I just ask it to print the rows just to verify it does. And now I'm going to see if I can recreate the original matrix using this rank 11 approximation. And so that's what's happening here when we type in my A. So it's F of C, F of U times F of R. And those are the elements that were decomposed in the CUR decomposition for the rank 11 estimation. So, but now when this prints to the screen, you can see it's 15 by 15 matrix. Well, I thought you said it was a rank 11, right? So why is it telling us there's 15 by 15 dimensions? So if we go to the next page, I can take my A, and you'll notice I created my A here in line number 9. I did a difference calculation here just to see what the error was, but I think what's important for us to see now, as we're getting to the end of the slide series, is the rank of my estimation is right here on line number 8, and it tells me that the rank is 11. So apparently it did succeed, and there are some columns and rows in the prior version that could be eliminated. And so I think that's the extent of my slide today, and I appreciate your time and interest. If you have questions, I have a couple minutes. Yes, sir, you're at the top. So Julia they distribute binaries and open source for Windows, Mac, Linux, and probably any other thing you can think of. Good question. Anybody else? Dr. Seckman's nodding yes. Very good. Yes, sir? I guess it's possible, right? Dr. Seckman has done. There you go, PCA. Anyone else? Thank you, everyone.